Hello, everyone. I'll be speaking today about OAuth token hijacking in Google Cloud. My name is Jenko Wong. I'm currently a security researcher at Netskope, and I've spent my career in a variety of security areas at startups in engineering and product roles, covering some of these areas and topics. So in this talk, I'll be covering how session tokens on a GCP admin's client environment can be hijacked to gain access to that user's GCP environments. We'll also cover other risk areas like compute instances and service accounts that are both attack opportunities as well as concerns from the defensive side. And certainly we'll end up trying to determine what defensive measures work or don't work from a practical perspective across prevention, detection, and remediation. So why do we care? Well, essentially, hijacking of session tokens in GCP just provides additional attack vectors for persistence as well as evasion. OAuth is used everywhere in GCP authentication, both user accounts, service accounts, browsers, and SDK sessions, externally for client access such as CLI, as well as internal to GCP environment with compute instances. Particularly, it's problematic because they're cached, and that allows an attacker access to essentially existing authenticated sessions to environments without actually having to authenticate. From a defensive viewpoint, some of the stricter authentication controls, such as MFA, don't help, which can be counterintuitive. The options for prevention, detection, and remediation can be limiting, confusing, too numerous in some areas, and they also differ between what you might expect based on permanent credentials. They differ with temporary session tokens, and all of this can lead to confusion. And it may mean operations playbooks and scripts are out of date or have gaps. So really quickly, let's touch on OAuth. Many of us are exposed to OAuth as internet users. You might be granting access to Google Drive access or requests. You might be approving payments such as PayPal to third-party apps. From our perspective, because Google's chosen it, there are OAuth flows everywhere underneath the hood. We don't see it all the time, but we do see some of it. The first time you use a CLI with a configured account, it may prompt you to pop open a browser and approve a certain set of privileges. And you have to type in a code and so on and so forth, and then your CLI will work. So the first step is whatever's requesting access, in this case it's the CLI, requests a token, which really means an access session token and a refresh token. We'll cover how those are used later. But the access token, sometimes called a bearer token, is passed in the HTTP header for an actual REST API call. After an hour, it expires, at least that's its default timeout, and then the refresh token is used to receive or create a new fresh access token that can be used. Most of this is just done underneath the hood by, say, the gcloud CLI, and you don't see that as a user except for the very initial approval and authentication step. We're going to now look at an attack scenario, which is what I describe as bulk copying of credentials and using them quickly and easily within the CLI. This does assume that we have compromised an endpoint, in this case a GCP admin user. That, I'll posit, is feasible enough that it's an okay starting point. We can find GCP users easily on the internet. We can find companies that host in GCP. We can deliver various payload, say, wrapped up in open source utilities. So if you will, let's use this as a starting point, since I won't be focusing on the actual compromise, but more what happens once you have access to that client machine. Well, what we'll show is that it's straightforward to access any cached accounts in GCP environments. It's also easy to copy those credentials in bulk to offboard to another host that's controlled by the attacker, and then access those same accounts. So let's go through that. I have a screen with two sort of split windows, two host sessions. One on the left is the target host or the victim's host, where the GCP admin does work with the CLI. The right host is controlled by the attacker, different hosts that we'll use later. So as we go through this, first thing you'll note is I'm checking with gcloud auth list what configured accounts there are. There's two accounts, production account as well as a dev account. So just a quick note on this session. This is a recorded session, but these were live environments configured with reasonable security policies. In this case, MFA was on both, and hardware MFA on the production environment. Also, any output has been scrubbed for PII, so there's just remapped account IDs, names, tokens, etc. So I'm going to switch accounts to that admin prod account. Okay, we can see that in the output of gcloud auth list, that the asterisk shows what's active. And now I'm going to take a look at what I can access. Remember, I'm on the victim's machine. I've compromised it. I have at least their user privileges. And yes, it makes sense that I could execute gcloud commands. I can see the project, one of the projects here. I can also list the buckets within that project and then list items in that bucket. Okay, so that was really easy. Let's continue on to our next step. That was step one of just reusing the credential cache on the victim's machine. But now what I want to do is I want to go to the credential cache and copy it to a different machine on the right side, my attacker machine. In the home directory in .config gcloud is the credential cache. We'll cover the details of those files later. But I'm just going to tarball it up and then SCP it over. Then on the right side, I'll continue on. And I'm going to find that tarball. I'm going to CD here in the bottom right to my own .config. All right. Notice as well that I did check that there were nothing pre-configured. gcloud auth list returned nothing. Now I'm going to untar that credential cache in my own .config directory. And now I check again with gcloud auth list, and suddenly my configuration has changed to match what's in that tarball, which is the two accounts, prod and dev. And that was pretty easy. Let's see if they actually work. So I'm going to switch accounts. Let's pick that production account. And then I'm going to use gsutil, which uses the same credential cache as gcloud, to list the sensitive bucket, and boom, I get results right away. So that was easy. The point here is that there's no encryption, there's no signing, there's no tying of the credential cache to a particular host. I was able to move it off board and reuse it just as easily as on the victim's host. Now, a variation of that attack is to actually peel back the layers of the credential cache and extract OAuth tokens. And so we'll use some SQLite commands. We'll then perform the OAuth flow and request a new access token, which will be good for an hour. Then we'll make API calls. So let's see what that flow looks like. So I'm going to move back to the victim's machine. And bear with me, I'm going to list the contents of the .config gcloud directory where the credential cache is, and I see a bunch of files and directories, of which the .db files are SQLite files, database files. I'm going to actually use the SQLite command line to access one of the database files. The access tokens database file has one table in it, and as its name implies, it has access tokens, and I can extract the access token for the admin user in the prod environment. I'm going to now look at, sorry, give me one moment to back up. I'm going to look at the other SQLite database file, the credentials DB. And here I have more information. I'm also going to query for the admin user in the prod environment. I get a bunch of JSON, including a client ID and secret, which is OAuth information that's needed to perform the OAuth flow, which is what we're going to do in this scenario. I have the refresh token also needed, and I also have the access token. So this is actually much more complete information and useful. So I'm going to just make sure I parse out the refresh token here at the bottom. I'm then going to use that in a REST API call to get a new fresh access token. Let me pause this. I know there's a lot here, so I'm going to point out in the middle. My curl command is right here where my cursor is. I pass in the refresh token, and what I get at the bottom is some JSON that includes a newly generated access token that expires in 1 hour. And my scopes are part of the request, and they're also returned with my results. Okay, now that I have an access token, I can now execute API call. So I'll do a bucket call, and we'll pause in a moment to take a look at that call. And the point here is all of these commands are curl commands, pretty straightforward way to do simple REST API calls. Here is the curl command. I'm passing in the new access token as a header. I'm hitting an endpoint and listing the contents of the bucket called sensitive bucket, which is the same bucket we accessed in the first scenario. And you can see from the output that I'm getting credit cards as a subdirectory, and I can see all the same information that I'd seen with the gcloud CLI. So that's how easy it is to actually peel back the layers. We can query those SQLite database cache files, extract tokens. The refresh token is the most important. I can generate new access tokens and go from there. It's more general, functionally similar to the CLI, but it's more general because I can use custom API code to do what I need to do. There are other attack opportunities as well as concerns. So we need to be aware of service accounts. Service accounts can be configured in the gcloud CLI just like user accounts. Sometimes administrators want to perform tasks as service accounts. They would download an API key file with the actual credentials, and then they would configure the CLI with that account information. Normally, an attacker would first look for the key file since it has the permanent credential in it, but there are reasons why they would still go after the credential cache, the SQLite database. One, it's another attack vector, but two, some of the remediation steps with session tokens are more difficult or more confusing than with permanent accounts, service accounts or keys. Meaning if you use that session token, it can be more difficult to defend against. It does have potentially an expiration time if it's been set, but at a minimum it's 1 hour, and that is plenty of time to do damage or install backdoors. So service accounts have to be kept in mind, even though people think about OAuth tokens as very much an interactive kind of authentication flow. Compute instances use service accounts. There's default service accounts, and you can use your own. There's no credential cache per se, but there is a metadata service that returns the current access token, and that's often the target for once a compute instance is compromised. It's the target in order to get a credential to move laterally within the environment. So that has to be thought about. It's an opportunity to attack, and it's an area of concern to defend against. The commands to do that, one, to query this actual metadata service is pretty straightforward. It can be done with a curl command on the run on the actual compute instance, and you can see that the access token highlighted in blue is returned. And then you can do a real API call with that access token, and you are now executing a command as the service account that the compute instance runs under. And this one, I just ran a bucket listing again, different environment, but I get actual files back. So speaking of compute instances, we started the attack scenarios with external client environments, external to GCP. Certainly compute instances that have Google Cloud installed have the same issues that we've talked about. So everything applies. So additional attack opportunities are compute instances where the CLI is installed. The thing that may not be on the radar for many is GCP managed compute instances that have this SDK installed. Very specifically Cloud Shell environments. Part of its value is it's pre-installed. You don't have to worry about it and manage it. And part of the opportunity is it inherits any potential issues, such as session token hijacking. Juan Berner wrote a good article about persistent GCP backdoors. I encourage you to read it. And he talks about hijacking the credential cache through a persistent backdoor on Google Cloud Shell environments. So let's talk about prevention. Number one, you do want to set an expiration time for Google Cloud SDK sessions, which really means CLI and API sessions. By default, there is no expiration, and that was the case with environments in the attack scenario. They were for months, cached accounts were accessible from that victim environment. You can set the expiration time. We'll go through that. You should also see if you can implement IP allow or whitelists. And if you have expiration time set, MFA increases the security of the reauthentication step. And when you go through IP allow lists, don't forget to think about compute instances as well as enforcement. So let's talk about these in more detail. So the cloud session duration is set on the G Suite admin side, and I want to raise that as a bit of a flag, yellow flag, that it's a different product, different set of APIs than the GCP suite. It's in the identity side. By default, it's set to never expire, but you can set the session duration to 1 hour up to 24 hours. Once the session expires, you can specify the reauthentication method, hardware security key or password. If you happen to have an authentication method that uses software-based MFA, then you'll have to choose password. So it's a little bit less secure. But in general, you want to set these. There's no reason not to. The default is not that secure. How do we set up IP allow lists? Create an access level with the IPs or site ranges in the access context manager in GCP console or the API. Create a VPC service control so that we can set up a boundary that references that same access level. And then apply it to the right VPC. And the next time someone tries to execute an API call against resources within that boundary, they'll get a 403 error. So that works as you would expect. But there's more involvement. If you have VM instances, you have to worry about those IP addresses. If they're executing API calls, remember they have potential compromise of OAuth tokens or session tokens, on VM instances. So IP allow lists have to include the IPs of those VMs. So if you have a small number of VMs, a small environment that has static IPs, you can probably hard code the IPs and maintain your IP lists. It's more problematic if you have a larger number of VMs, more dynamic environment with a lot of dynamic IPs. In that case, you may have to figure out how to automatically maintain the IP allow lists by hooking into the startup or provisioning process of VMs. That is overhead, that is work, but could very well be worth it to gain the benefit of the IP whitelisting. There's been some related work for AWS, not GCP, by the Netflix security team. And I encourage people to read that for good ideas for approaching that could be applied to GCP. IP allow lists do have to be enforced and checked. So through the CLI or API, you could roll your own checks, essentially to make sure that the definitions of the access levels have the right CIDR ranges and aren't drifting, that they are included in the right VPC service control definition, and that ultimately that service control is also applied to the right resources or VPC. MFA, highly encouraged to use that if you can manage it. It's on the G Suite admin side, so again, note there. And it governs or will govern the reauthentication step. So it only applies if you have session duration timeouts set. My attack scenarios that was not set, which is why we never encountered MFA. But once you set it, MFA will apply to the reauthentication once something times out. Now let's talk about detection. Behavioral detection is difficult, and compromised credentials is essentially a behavioral problem. Try to distinguish activity from the actor who has the compromised credential versus the valid user who got compromised. And having a general solution there is difficult, which is why a lot of the ML approaches have very specific use cases. So instead, I'm going to suggest maybe one or two simpler and hopefully more achievable ways to improve detection. One is really work hard to use IP allow lists in the prevention stage. If you do, then you could set up detections against failures in authentication from IPs that aren't in that list. So any failures due to the IP allow list could be good indicators of credential compromise. There is a chance, of course, of false positives. It depends on your user base and your ability to maintain the IP allow list. So if you can shrink your allowed IPs to a smaller range, that might include requiring VPN access or proxy access to access your GCP environments, then that IP allow list might be a smaller set of static ranges, and it may make detection against that list reliable with lower false positives. You may need to train users, but although it comes with overhead, it's definitely worth considering. On the right is what you would expect, but you will get clear error messages in Stackdriver from failures against the IP allow list. Another step that I think is worth entertaining is to populate fake accounts or breadcrumbs in the credential cache. Essentially provide an easy way to configure fake accounts. Attacker most likely will cycle through all accounts should they compromise the machine and look at this vector. And in trying every account, they'll try the fake account. And that has a much better chance of low false positives. And those could be easily detected and alerted upon. And there is some provisioning maintenance overhead, but since it's a SQLite database, let's turn that into an advantage. It'd be easy to have a simple script. You could have a 3-line shell script that inserts a fake credential into every credential cache. It just has to be run once. Train your users not to use it or delete it. And it'll survive upgrades of the G-Cloud SDK. So consider that as a higher fidelity detection on compromised credentials. Let's spend some time on remediation options, since this is both complicated and confusing. There are a multitude of options that we'll go through, but what I want to point out up front is there are two dimensions to worry about. User accounts are different in behavior than service accounts from a remediation viewpoint, so we have to look at them separately. We also have two steps to worry about. Locking out an account, that is locking out an attacker from future access to an account, is one step, but also revoking their current access, their current sessions, is very important. So let's go through this matrix. Here are the 3 basic steps that most people are aware of for dealing with locking out account access for user accounts. In G Suite Admin, I'm highlighting that user account management is in the G Suite side. You can find those options, and they're also available in the APIs for G Suite Admin. And so the bottom line is they all work. Let's suggest that the lowest impact, which is reset password, is our suggested remediation option. Nothing wrong with that. How about for service accounts? Well, similarly, there are 3 options. They're found in the UI under IAM service accounts in the GCP console. So remember, service accounts are managed in GCP, user accounts in G Suite. You can disable the service account, delete that actual key, and of course delete the service account itself. They all work, but we'll favor the least impactful one, which is deletion of API keys. Both of these are pretty standard, I'd say, in terms of practices. They work, and there shouldn't be any confusion. Where it does get confusing is how to revoke current sessions. Potentially, the same lockout procedures may revoke sessions, and we need to test that. But there are also session-specific functionality that I listed first, reset sign-in cookie, CLI, APIs, that need to be investigated. So, thankfully, I tested. You may be aware of this, but let's see if we can learn from my trials and tribulations. Reset sign-in cookies exists in G Suite Admin. Does this work? Unfortunately, no. It does work for web browser sessions. It does not work for SDK sessions, so it doesn't help our CLI vector. There is a CLI command, auth revoke, where you pass in an account name, as well as an API where you pass in a token. They do work, but not quite fully, and they're not viable. Why? What this CLI command does underneath is it looks up the account in the local credential cache, the CLI, the same one we've been talking about. It finds the OAuth session token. It calls the API, which then revokes the session token as well as the refresh token. However, those session tokens only exist on the client machine, which is the victim or compromised machine. And because it's compromised, we can't trust it. And further, an attacker can easily manipulate that and delete that token entry, preventing remediation using this path. The API call suffers from the same issue. That token that is required for the API call is only in existence on the client machine. It's not logged. It obviously exists on the GCP backend side, but it's not exposed to users through any API. So it can be manipulated. It's on a compromised machine. It doesn't help us. So why do these even exist, and why did I mention them? Well, I mentioned because they exist, but they're really self-serve steps for users to clean up their own credential cache. So what about our lockout account steps? Resetting a password does not revoke sessions, so it doesn't help us. Suspending and deleting a user account does invalidate sessions, but it's only during the suspension time. If you re-enable the user account, those session tokens start to work again until they expire, which is not the default. Deleting a user account does work. The sessions are revoked forever, permanently. It's just high impact. So these last two we could make work, possibly, but there's a better, almost ideal solution, which is in the G Suite admin side. There is a listing for each user of the connected OAuth applications. It just means it's a list of applications the user has approved, authenticated and approved, including the Google Cloud SDK. We've all seen this when you grant access, to Google Docs and Suite. This is the version for G Suite Admin. When I delete this, it immediately revokes all sessions, and this is not a permanent action with permanent ramifications. It just means the next time that the user needs to use the SDK, say the CLI, they'll be prompted to re-authenticate, and then the application will be listed here once again. So bottom line is this works. This is the recommended remediation step. But caveat is it lives in the G Suite admin side, and this is a bit confusing if you're not familiar with OAuth. So that's the recommended step. How about service accounts? Well, let's jump right into it. You think it's similar to user accounts. So it is in some respects. The CLI and the API call do not work. They provide more explicit errors. Some of those errors are misleading, filed bugs, and they are now partially corrected. But the bottom line is they were not made to work for service accounts, and that's usually the error you get. And no matter what, they don't revoke current sessions, so they're not useful, and they require access to the compromised client machine, which can't be trusted, and as well as can be spoofed by and manipulated by the attacker. How about the lockout steps for service accounts? Deleting the API key does not affect current sessions. Disabling and deleting the service account does work, but once again, we run into this temporary nature. So once the service account is re-enabled, the tokens work. So how do we make this work? And we're going to try to make this work because there's no similar delete connected app functionality for service accounts. You can make this work by ensuring you have a cloud session duration, which is a timeout on sessions. And you could suspend for a time period greater than that timeout. So let's say it's set to 1 hour to timeout. You suspend a service account, you wait an hour. When you re-enable it, any current sessions will have been timed out and invalidated. And of course, during the suspension, you change API keys. Sound confusing? That's because it is. How about deleting service account? It works just like deleting a user account. It just has high impact. So the bottom line is the best option depends on you. Can you recover from a disabled service account versus a deleted service account reliably and quickly? Which one gives you the fastest path to availability, knowing that service accounts may be widely used by compute instances? Not necessarily the right answer. At a minimum, you have to disable the service account for at least an hour or whatever your cloud session duration is. If you set to 8 hours, you'd have to be down for 8 hours. It could potentially be recovered quicker with the deletion of service account, but only if you're good at provisioning and keep up-to-date track of permissions and roles and everything else. So in conclusion, we've gone through sort of 5 different attack scenarios. External clients where the SDK is installed, both user accounts and service accounts. Internal environments like compute engines where the SDK is installed. But also the cloud shell environments which are managed by Google itself, but also have a cloud SDK. And within compute engines, outside of an SDK install, there's a more general problem where service account access tokens are available through the metadata service. So these are all opportunities in different vectors to attack, and there are also different areas that need to be considered and defended against. The defensive measures in all cases tend to revolve around this, and so this is a consolidated summary. Definitely set session timeout, implement IP allow lists, use MFA so that after a timeout, you have a higher level of authentication controls in place. Detect failed authorizations due to your IP whitelisting, as well as try to be proactive and install fake accounts or breadcrumbs in every CLI install by just manipulating the credential cache directly. And for remediation, sort through all the multitude of options and focus on the ones that work, especially for the current session access. Delete connected applications in G Suite is key, and then determine whether disabling or deleting service accounts is more reliable or quicker for you. And in terms of takeaways, hijacking authentication is not new, but cloud sessions is relatively new, and it's also easy to do. And just because they're temporary doesn't mean they're secure. You have to do the work to actually defend against that. And unfortunately, cloud vendors have done a poor job in tracking temporary tokens, or allowing clean revocation of these temporary credentials. And they really need to provide better support for prevention and detection. From a defensive viewpoint, though, there are concrete things we can do: session timeouts, IP allow lists, things that we just discussed on the previous slide. But focus on low false positive kinds of failures for detection. And test on the remediation side, where there's often many options. And if you can be organized within change management procedures, it will certainly help a great deal in the remediation area, because you can, at the worst case, delete and recreate resources to deal with current access. And just be very aware that within Google, G Suite versus GCP, they split responsibility for various security functions that are very important when you're in the middle of an incident. And that access and roles and responsibilities need to be sorted out clearly prior to any incident. Thank you. And now I think we have some time for questions.